You are falling toward the center of the Earth, right now. But there's no force pulling you down. And once you understand why, you'll never feel standing still the same way again. So every single day, you feel your weight pressing into your chair, the pull of Earth beneath your feet, that constant sensation that something is yanking you downward. But what if I told you that sensation you felt every second of your entire life is not gravity? What if gravity isn't pulling you at all, and what you actually feel is something Einstein predicted that nobody expected? What if everything you were taught about why objects fall was a simplification so extreme it became fundamentally wrong? Everything you learned in school about gravity was designed to get you through exams, not to tell you the truth. Newton's falling apple, force equations with arrows pointing down, what goes up must come down. All of it simplified to the point where it described reality just well enough to be useful, but not accurate enough to be true. And the person who proved this wasn't trying to overthrow Newton. He was trying to understand why time flows differently on a mountain than in a valley. His name was Albert Einstein, and what he discovered changed physics forever. Here's what you believe about gravity, because it's what everyone believes. Massive objects like Earth create an invisible force that reaches out through empty space and pulls smaller objects toward them. The bigger the mass, the stronger the pull. The farther away you are, the weaker it gets. This force is why apples fall, why you have weight, why the moon orbits Earth and Earth orbits the sun. And this belief feels so obviously, undeniably true because you experience it constantly. Drop your phone, gravity pulled it down. Jump off a step, gravity pulls you back to the ground. Stand up right now, and you feel it. That downward sensation, that weight, that pull. Your entire nervous system has been shaped by evolution to navigate this force. Your muscles compensate for it. Your inner ear balances against it. Your proprioception, the sense of where your body is in space, is calibrated to it. So when someone says gravity isn't a force, your brain rejects it immediately. Because if gravity isn't pulling you down, then what are you feeling right now? This is the grip of Newtonian gravity. It's been the dominant model for over 300 years. It works. It predicts planetary orbits. It launches rockets into space. But working and being true are not the same thing. In 1907, a 28-year-old patent clerk in Bern, Switzerland, was sitting at his desk when he had what he later called the happiest thought of my life. His name was Albert Einstein. And the thought was this: if a person falls freely from a roof, they don't feel their own weight. That's it. That was the insight that shattered 3 centuries of physics. Think about what that means. If you're standing on the ground, you feel weight. But if you're in free fall, skydiving, elevator cable snapping, astronaut in orbit, you feel weightless. Einstein realized something everyone had missed. Gravity only seems to exist when something prevents you from falling. The sensation you interpret as gravity pulling down is actually the ground pushing up. But if that's true, then what is gravity? Einstein spent the next 8 years wrestling with this question. He taught himself advanced mathematics. He abandoned dead-end theories. He collaborated with mathematician Marcel Grossmann. He filled notebooks with equations that looked nothing like Newton's. In 1915, he published his answer, the General Theory of Relativity. And it was more radical than anyone expected. Gravity, Einstein proposed, is not a force at all. It is the curvature of spacetime. When the paper was published, even physicists who understood the mathematics struggled to accept it. It violated intuition at every level. But Einstein had made specific, testable predictions. And in 1919, British astronomer Arthur Eddington traveled to the island of Princep off the coast of Africa to observe a total solar eclipse. According to Newton, light from distant stars passing near the sun should bend slightly due to gravitational pull. According to Einstein, light should bend twice as much because space-time itself curves around the sun. Eddington measured the positions of stars during the eclipse. Einstein was right. Newton was wrong. Overnight, Einstein became the most famous scientist in the world. But the question remained: if gravity isn't a force, then what the hell is it? Imagine space-time as a fabric. Not just space, space-time,
4 dimensions woven together, 3 dimensions of space, 1 dimension of time. In the absence of mass, this fabric is flat. Objects moving through flat spacetime travel in straight lines. Time flows uniformly everywhere. But when you place a massive object into spacetime, say the Earth, the fabric warps. It bends, it curves, it deforms around the mass. Now here's the key. You are not standing still. You think you're stationary because you're not moving through space, but you are moving through spacetime, specifically through the time dimension, at the speed of light. Every second, you advance 1 second into the future. That's motion. That's velocity. 299,792,458 meters per second through time.
And because Earth's mass warps spacetime, your path through time curves toward the center of the planet. Imagine rolling a marble across a flat table. It goes straight. Now press a bowling ball into the center of a trampoline. The fabric curves. Roll the marble again, and it curves toward the bowling ball. Not because the bowling ball is pulling it, but because the surface itself is curved. That's what's happening to you right now. Earth's mass has curved spacetime so severely that your natural path through time, your geodesic, the straightest possible route through curved spacetime, bends continuously toward Earth's center. You're not being pulled down. You're falling freely along the curved geometry of spacetime. The ground is in your way. And because the ground, made of atoms held together by electromagnetic forces, resists your motion, it pushes up against you. That is what you feel as weight. Not gravity pulling you down, the ground pushing you up, preventing you from following your natural path through curved spacetime. If the ground vanished, you wouldn't feel gravity. You'd feel weightless, because you'd be moving freely along the curve. Just like astronauts in orbit. The International Space Station isn't beyond Earth's gravity. It orbits just 400 kilometers up, where gravity is still 90% as strong as on the surface. But the astronauts are in free fall. They're following spacetime's curvature. Nothing is in their way. That's why they float. You, right now, are doing the same thing they are. The only difference is the ground is blocking you. Gravity doesn't pull. Space-time curves.
If this sounds like abstract philosophy, here's how we know it's real. In 1971, physicists Joseph Haefele and Richard Keating flew atomic clocks around the world on commercial airplanes. When they landed, those clocks had aged differently than clocks that stayed on the ground. Not malfunctioned, aged differently. Because time flows at different rates depending on how curved spacetime is. Then came GPS. Every GPS satellite orbits at 20,000 kilometers altitude, moving at 14,000 kilometers per hour. According to Einstein, 2 things should happen to the clocks on board. 1, because they're moving fast, special relativity says their clocks should tick slower than Earth clocks by 7 microseconds per day. 2, because they're farther from Earth's mass, spacetime is less curved, so their clocks should tick faster by 45 microseconds per day. Net effect? GPS clocks run 38 microseconds faster per day than ground clocks. That sounds insignificant, but GPS relies on nanosecond precision. If engineers didn't correct for relativity, your GPS would be off by 10 kilometers after 1 day. Every time you navigate with your phone, you're proving Einstein right. In 2010, NIST physicists measured time dilation over a height difference of 1 foot. They placed 2 atomic clocks 30 centimeters apart, vertically. The higher clock ticked faster, measurably, reproducibly. In 2024, researchers at JILA in Colorado measured it at the sub-millimeter scale, about the thickness of a human hair. Space-time curvature isn't theory, it's engineering. And then in 2016, the LIGO experiment detected gravitational waves, ripples in space-time itself, caused by 2 black holes colliding a billion light-years away. Einstein predicted those waves in 1916. It took a century to find them. But they're real. Spacetime isn't just curved, it's dynamic. It bends, stretches, vibrates. It's not a stage where physics happens. It's the medium through which physics happens.
So why does every human being instinctively believe gravity is a force pulling them down? Because your brain evolved on the surface of a planet with 1 g of constant space-time curvature. You never experience flat space-time. You never feel true weightlessness. From birth to death, the ground is always pushing up against you. So your brain builds a model. Something is pulling me down and the ground stops me. That model is wrong, but it's useful. It predicts what will happen when you drop an object. It keeps you alive. Evolution doesn't care about truth. It cares about survival. And the truth that you're perpetually falling through curved four-dimensional spacetime while the electromagnetic forces between atoms and the ground resist your geodesic motion is not useful for catching prey or avoiding predators. So your brain simplifies it to gravity pulls things down. And that simplification becomes so embedded, so visceral, so confirmed by daily experience that when someone tells you it's wrong, it feels like an attack on reality itself. But it's not. It's just physics being weirder than evolution prepared us for. Once you understand this, everything changes. Because if gravity is space-time curvature, then time is not absolute. Two people can experience different durations depending on where they are. Simultaneity depends on motion. Events that are simultaneous for you might be sequential for someone else. Black holes become inevitable. If you compress enough mass into a small enough space, space-time curves so severely that not even light can escape. The universe itself is dynamic. Space-time can stretch. That's why galaxies are receding from each other, not because they're moving through space, but because space is expanding between them. Even the concept of now becomes relative. The universe doesn't have a universal present moment. Your now is different from someone else's now if you're moving relative to them. None of this works if gravity is just a force. All of it follows inevitably from curved spacetime. So remember when I said you're falling right now, but there's no force pulling you down? Now you know why. You're not standing still. You're moving through time at the speed of light. Earth's mass warps spacetime. Your path curves toward the planet's center. The ground pushes up, and that resistance is weight. The next time you feel gravity, remember, you're not being pulled down. You're falling freely through the curved spacetime around a massive object, and the ground is in your way. Einstein saw this, and once you see it too, you can't unsee it. If this changed how you see gravity, hit the like button